Welcome to June 24th LeetCode Challenge. Out of boundaries paths. There's an n by n grid with a ball. The ball initially starts the position start row, start column. You're allowed to move the ball one of the four adjacent four cells in the grid, possibly out of the grid, crossing the grid boundaries. You can apply a most max moves to the ball. Given the 5 integers m, n, max move, start row, start column, return the number of paths to move the ball out of the grid boundaries. Since the answer can be very large, return the modulo 10 to the 9 plus 7. So you see here, you're given a m by n matrix, grid. So you have 2 by 2 grid where the maximum move is 2, you start row is 0, and start column is 0. So I start with this corner here. So at maximum 2 moves, it means you can move two times or 1 time. So moving 1 time, you're able to get out to the grid boundaries by moving up once, or moving to the left once. Then you also have the boundaries. However, if you use 2 moves, you can go down once and to the left once to get out of the boundaries, then down to get out, then right, up to get out, and right. So in total, you have 6 possible moves. 6 possible ways to get outside the boundaries of the grid using maximum 2 moves with these conditions. Let's go for example 2. This time, if the grid is not square, we have a 1 by 3 grid where start row is 0, 1, column 1. Start row 0, column 1, which is in the middle here. So you have maximum 3 moves this time. So with 1 move, you can go up or down to get out. With 2 moves, you can go to left, up, left, or down to get out of the grid. And then you have starting at 0, starting at the initial position, you can go right, up, right, down to get out of the grid. And then when you use 3 moves, you can go to the right and to the left, then back to the right, then up and down. And then from here, you can go from to the right, then back to the left, up and down. So you have 12 possible ways to exit the grid using these parameters. So if we think about it naively, using the brute force approach, we could take 1 step in every direction and decrement the numbers of max moves it could take for each step. So whenever reaching outside the boundaries while taking a step, we could deduce that we have an extra path available for us to take the ball out. So in order to implement this, we need to use a recursive formula, function, as I say. It's kind of similar to like a depth first search algorithm, so I'm going to define it naively. It might not work due to a time limit exceeded type of function, but because the time complexity would be quite huge. But let's figure it out and at least start it so we can have some good footing. So we'll take in our this is our boundaries. So we define, let's say, ij for our positions of where we are. So we're given our start position, our m, which is our m, and n, which is our grid. So we want to be able to traverse our grid with I and j. Then we want to keep track of the numbers of moves we have already done. So let's call that u. So what are conditions to return? So if we are taking a step, so if we have our I, our index of where we are in our what's called our row, if the row is less than or equal to 0, or the row that we're on is greater than or equal to our start row, start row, then we want to return 1. Or if our position on our column is less than 0, or our column that we're on is greater or equal to our start column, which is n. So that's true. Return 1 because we can only make 1 move. Else, if the number of moves is less then or equal to 0 left remaining, then return 0 because we can't get out of the grid. So now we want to return a depth first search algorithm, so DSF. Okay, now we're going to move in the I-1 direction index with J staying the same and decrementing our moves. We want to also combine that with I+1 direction with J staying the same, decrementing our move. Now we want to move in the J direction. I stays the same this time. J-1 direction, decrementing our move, plus our DSF for our I stays the same, J+1, decrementing our moves. Then we want to return our for search algorithm with our initial starting point, so start row, start column, max move, and then take the modulus of that with 10 to the 9 plus 7. Let's run the code. Oh, there's something wrong here. Let's see. Oh, we don't want it equal or greater than m or j less than 0. Return 1. Yes. I+1, I-1, J-1, J+1. Let's see, take the modulus, 10 to 9. Okay, that seems to work. However, if you were to run this, you will have a big O of n, big O of 4 to the n times. So that will make give you a time limit exceeded. However, there's a small trick here. You could use a least recently used cache. A small trick here just to make sure that you're using the least recently used cache and caching everything instead. So it's kind of like a cheat to the memoization. So let's submit it to see if this works. Okay, accepted. So this is using a brute force algorithm with using the least recently used cache. It's kind of a cheap way of doing it, but it's as a method. I did think of another solution for this, by the way, so I'm just going to show it here, since the video is already getting quite long. I won't go through that much. So instead of using the least recently used cache, I'm going to use a dictionary instead. And I'm going to keep, instead of using return statement that gives us all 4 of these in the same line, we're just going to break it up into individual components. And let's, we can leave this the same. We can, let's see, what are we going to define now? So, let's see, if we are going to find a depth first search algorithm with a dictionary inside, call it D. And then we're going to take our parameter there. Alright, so let's kind of redefine this aspect. We'll keep the majority of it. So let's kind of erase all this for now. Alright. So if I, J, and U is in D, what we're going to do is return D at index I, J, U. So this is kind of using recursion with memoization with the dictionary. However, if the U is not 0, what do you want to do? So we're going to do some ternary operators here. So we're going to do what's called Let's call this results equals 0. So if results plus equals to 1 if I minus 1 is less than 0. So this is what we did before, except we're doing it in one kind of one line ternary operators now. Else the first search algorithm for it's pretty much this with a dictionary inside. Same deal, so results plus incrementing 1 if I plus 1 equals m, else. I'm going to copy this now. That first serial algorithm for a dictionary. I'm going to need this later. Results plus incrementing 1 if j minus 1 is less than 0, else depth first search algorithm of our dictionary with the dictionary inside. Oh no, I control that. Put that there first. Alright, and then we want to result incrementing 1 if j plus 1 is equal to n. Else, return that. And then what do you want to do? We want to, at the end of this, reassign our dictionary at I, J, U, P, R. So we could recursively do that again. Then we want to return R, else return 0. Okay, let's see if this works. Results. Alright, let's see if this works. Accepted. So yeah, this is kind of using memoization. It's using a dictionary to keep to store our cache instead of using the least efficient use cache type system. And if I had to break this down to time complexity, I would say it's be big O of n times m times the number of max moves. So yeah, it'd be big O of n, m, n, and big N, because we do save everything inside a dictionary. And the space complexity is also the same, m times n times max move. Alright, there you go. Have a nice day.